Hello, we're here at the University of New South Wales. I'm Norman Wahlberger, and we're going over some first year linear algebra tutorial problems. This is a problem in linear algebra. We're asked to do a bit of manipulation with complex numbers. We've been given two complex numbers, z and w. We're told that 2z plus 3w happens to be 1 plus 12i, and z bar minus w bar is 3 minus I, and we're trying to find what are z and w. All right, so here's a solution. So first, let me recall that if z equals a plus bi, then its complex conjugate, z bar, is a minus bi. That's the definition of z bar, called the complex conjugate. And I guess the main things that we want to know about this complex conjugate is things like if you have z and w and you take the complex conjugate of the sum, then you get the complex conjugate of z plus the conjugate of w. Or if you take the complex conjugate of the difference, similarly we get the difference of the complex conjugates. Another important law is that if we have the product of two complex numbers and we take the complex conjugate of the product, then we get the product of the individual complex numbers. In fact, that also holds for a quotient. So we have w over z. We're taking the complex conjugate of that. Then it's the complex conjugate of w divided by the complex conjugate of z. And perhaps I just should remind you also that pictorially in the complex plane, where we have a 1 here and an I here, real axis and imaginary axis, then if we have some complex number z equals a plus bi there, then its complex conjugate is essentially the reflection in the x-axis. So the x component A stays the same, but the y component B negates. Okay, so now we can go to our problem and ask, okay, how are we going to take these two equations and manipulate them so that we can get z and w? Okay, well, since z bar minus w bar equals 3 minus I, that's an equation involving z bar and w bar. We would rather have an equation involving z and w, because then we could combine that with the equation that we already have there involving z and w. So one way of doing that would be to take the complex conjugate of both sides. Then, if we use this fact here, we're going to get z minus w instead of z bar minus w bar. So since z bar minus w bar equals 3 minus I, z bar minus w bar bar equals 3 minus I bar. So if these two things are equal, then if we take the complex conjugates of both, they're also equal. And that tells us that z minus w equals complex conjugate of 3 minus I is 3 plus I. Okay, so we're basically using this fact here together with the fact that the complex conjugate of the complex conjugate is the original thing. Maybe I didn't say that. Perhaps it's worth mentioning. But if you take the complex conjugate of z and then you take the complex conjugate of that, well, you're going to get the z back again. Okay, that's what we're doing here. So we're combining this one with this one so that the left-hand side becomes a z minus w. All right, so now we have this equation. So combine this with the first equation that we have, which is 2z plus 3w equals 1 plus 12i. So how are we going to combine this equation and that equation to find out what Z and W are? Well, this is a situation of two equations and two unknowns. Very basic, kind of important, motivating example in linear algebra. And the idea is that we're going to just, in this case, make some manipulations to eliminate one of the variables. All right. So if we call this equation, say, 1, and we call this equation, say, 2, then what we can do is we can, say, multiply equation 1 by, say, 3, and add it to equation 2. That will get rid of the W terms. So we'll take 3 times equation 1 and plus equation 2. All right. So what's that going to give us? So we get to have 3Z minus 3W plus 2Z plus 3W equals 3 plus I, if we have to multiply that by 3, so it's 3 times 3 plus I plus 1 plus 12I. Okay, you can see that I'm combining this equation with that equation. I'm multiplying this equation by 3, adding it to that equation so that the W's now cancel. We're now only going to be left with 5Z on this left-hand side. And on the right-hand side, let's see, we have 3 times 3 is 9 plus 1, that's 10. And the imaginary parts, 3 times I plus 12I, that's altogether 15I. So therefore, we see that Z dividing by 5 is 2 plus 3I. And then, well, we have to solve for W, so we could probably go back to this equation 1. Now, sub into equation 1 to get 2 plus 3I minus W equals 3 plus I. So that, let's see, bringing the numbers on the left-hand side and the W on the right-hand side, we get minus 1 plus 2I equals W. All right, so altogether, we'll summarize our results. So Z equals 2 plus 3I, and W equals minus 1 plus 2I. And there we found Z and W satisfying these two equations.